So that's typically how we do it. So, air filter. So if you've noticed the upgrade on Mike Marshall's, he has pretty close. He's in between the 285 Bravo and the 290. He's not full-blown 290 yet, but he's really close. You'll notice the air box on his is different than the air box on the other two 290s. The other two 290s are the upgraded air box because we have the mass flow air sensor on it. So we've had to change some things around. You can still, if you want to go with the Bravo model, you can still run the older oval style if you like, because you're not going to be running the mass flow air sensor because you haven't upgraded to the new ECU. So you have the option to do that very early on.
You died.
I stepped on it. Anyways.
Commercial break.
If you have the old early 285, there's no air box at all on it. And they run fine. The thing is, if you put an air box on it, it's quieter, and it also gives you something to mount the ambient air temperature sensor into. So it's not, if you do the half upgrade, the Bravo model, I would still recommend doing that air box. Hello? Got it? Okay. Then the 290 model. So now the 290, this is the full blown, this is what's going to happen on any 290 model as of right now. It'll be the gear change, obviously, so it'll be a 7,000 RPM engine at 100%. The air intake system, it's got the added mass flow, ambient air, and the filter box is different. The air intake, it's, you know, you just can't put an air intake on a two-stroke. Just to go back here a little bit of a second. Two-strokes work off of airflow. And it doesn't matter if it's the intake, the exhaust, the ports, whatever. If you disturb the airflow in any way, they just don't run very well. It's just the nature of a two-stroke. So an air box is very important. It has to be designed so as you have pulses coming in and out of those two cylinders, they can't interfere with each other, because one will play with the other cylinder, and then all of a sudden it's misfiring, carrying on. One will run hot, one will run cold, it'll do all kinds of crazy things. So the air boxes, both of those air boxes work very well. We've actually tested them to prove that we're not messing with the airflow on the engine in the way that it operates. So that part has been tested as well. So if you've got a 285 and you go, hey, I got an idea for an air box, I want mine to look like a coffin. Well, it might turn into a coffin. Just remember that. You know, you just can't change things when it has to go with airflow. Just like the exhaust. If you want to dream up an exhaust, obviously it's experimental. You can do anything you want. It's your aircraft. You can do anything you want. Just be cautious about it and do your testing baby steps. Baby steps, baby steps. So, but currently the exhaust system we have is working perfectly fine. As I said, stepped up on the pipe at 6,300. If you're flying at 7,000, you're well above it. So you should never get in any of that oscillation of stepping up, stepping down, any of that stuff. So I would just keep the stock exhaust you have. Throttle body flow, we talked about. We do all of that before we build them, if they're built here. Flywheel balancing as well. Alternator has the new one. Now, when we do the alternators, which is a little bit different than what the one that comes off of it, we shield the entire alternator system all the way up to the regulator as well. It's bonded and grounded and shielded. That should help a lot on your avionics, your radio interference, and things of that nature. Although currently, I don't think we got a, we haven't had a problem with the radio in the 290, right? The URL. I mean, when I started on it seemed fine. I'm half deaf, so. But anyhow, that is something that we do too. So if you were to do the 285 Bravo update, you change that alternator. That's something we would supply, but you would need the directions on how to do that. Some of you may or may not know when you shield something, you can only ground one end of it. You can't ground both ends. If you do, you're going backwards. Now it's a ground loop, creates all kinds of problems. But we'll give you the directions on how to do that if you choose to do it yourself. Just a side note. What was that? Yeah, well, this is something that me and Matthew keep passing the night on. I was trying to get from him. He gave me a piece of paper. I'm like, what? I couldn't read his piece of paper, but maybe. I was trying to give how many optional. So the new ECU is capable of much more than what we're using it for. So there's extra ports for data input on it. Matthew, I'm going to try to ask you this question. If you don't know it, then fine. But there are extra ports. There's digital and analog. Is that correct? Do you know how many that we're not using? That we don't use, that are available?
Depends on if you have the field pressure sensors, but...
Well, that would be considered part of it.
There's 6 analog 0 to 5 volt inputs, 2 analog temperature inputs, and 4 digital inputs. So,
Okay.
4 digital, 8 analog.
Did everybody hear that?
4 digital, 8 analog 0 to 5 volt inputs, and a lot more outputs as well.
Right.
That we don't
So if you don't know what any of that means, basically what it means is, say you want to add another sensor. Say you want a fuel pressure sensor on it. It's fuel injection. It's nice to know what your fuel pressure, your rail pressure is. You can put a sensor in there, wired directly into that thing with the CAN bus. You can run that. You don't even have to run wires up to the dash. If you get the EFIS dash, you just create on the EFIS panel another gauge. Boom. It's that simple. So there's several optional ports to do all kinds of sensors and stuff with. And so there's plenty of room to grow with that thing if you want to grow with it. You can, to push it, we haven't done this yet, but to push that EFIS panel even further and that ECU, that aircraft can be made where there's no keys, no switches, no buttons. It's all on the dash. It's a touch screen. You hit it, it lights up. You put in your secret squirrel code that you know. That's your key. It lights up, and when you want to start it, you can just find the button on this touchscreen panel and hit it, and the thing fires off. I mean, that's how far you can push this if you want to. Currently, our test models, we don't have them set up that way, but Matthew, you correct me if I'm wrong, it's not a huge stretch to get there if somebody wanted to do it. It's all feasibly possible. Testing, okay, in-house. Jimmy's going to come up and talk when I get done here, but I just wanted to briefly go over some stuff, some of the testing we've done. We've got new blades on 3 birds flying. The blades, we're very happy with the testing. We've done some testing here in-house. We've done group testing, SAG testing, torsional testing. What we have to compare with is what our old blade we used, which was Ernie Boyette's blade. And so the goal is we wanted to meet or exceed any standards that was on that blade, because it was a very fine blade. Flies very well. There's no complaints whatsoever with that blade, just to be clear. We ended up doing some digital analysis of Ernie's blade and found an anomaly in the blade. It turns out that the bottom side of the blade actually had a concave hook in it. It was small enough that you couldn't see it visually, but digitally it was there. So we were able to redraw that blade, redesign it, and get that out of it. And the difference between that little tiny hook that you couldn't see in there and not being there was, in the wind tunnel test, the blade actually goes to 1 full degree more before the blade stalls, which is interesting. However, on the other side of the coin, during, I call it compression lift, I don't know what Jimmy calls it, but I consider blades have 2 kinds of lift. You have compression lift. If you take a sheet of plywood and you held it at an angle and you could spin fast enough, you're going to get some lift out of it, right? It's not an airfoil. That I consider that compression lift, right?
Okay.
So the concave on the bottom of that blade, ever so slight it was, that was adding to the compression lift. So when you look at the wind tunnel test, the new blade stalls at a much higher angle of attack, but on the lower end, lift comes in at a little low, 1 degree less. Yeah. So what it did is it just moved that 1 degree up 1 scale. Well, we want it up here. We don't want it, because we're not flying down here anyways, right? Flat pitch or negative pitch, we're not flying there anyways. So that's probably the biggest difference as far as the airfoil change goes. As far as the NACA number, it's pretty much the same. The trailing edge, which is referred to as reflex, it's a little longer. So the blade is a bit lighter on the collective. There's less collective pressure on it. The blade as a whole is about 1 pound heavier than the older blades, but the blades are much better matched. And it just has to do with the manufacturing and production. If you go over to the blade building in the front, that's where the blade production is happening. There's a CNC machine in there that we build, along with other machinery used to make the blades. But the tip weights, the doublers, and the spars in the blades are all machined. They're not hand ground like Ernie did. But, I mean, Ernie's, they work fine. But building the way he did it, he would make several tip weights, for instance, and he would hand grind them to fit into the spars. When he got done with a pile of them, he would weigh them all, and he would try to pair them up with two that weighed as close as possible. Did the same thing with the doublers. He would put the blade together, then he would put it on a bounce beam with a water leveler, and he would balance them before he even put them in the box and ship them to us or you, the kit builder. Even that he balanced them prior to you getting them, it would not be uncommon for us to, once you put them on the machine, you would have to rebalance them, and they would be anywhere from 4 to 10 grams out. You would have to sweeten them up. Not a problem to do. We just hung Dave's blades this week on his machine out there. 2 random blades that we made last week. Hung them on his bird. We did no pre-balancing on them. Put them on the bird. They were within 4 grams. So that's the difference in the manufacturing process of getting a more repetitive blade. You get a blade, it's more, so therefore, if you were to happen to damage one blade and you only needed one blade to replace it, not so hard to do now. But Ernie's blades, you got to buy a set, because the odds are what you're going to get is nowhere close to the one, and there's not enough meat in the blade to get it to balance out, right? So that's important. The other thing you'll notice about the blades, if you look at Ernie's blades, is a 3-piece blade, which is very, very common in experimental world. There's a top skin, a bottom skin, and a spar. Top skin is glued on the back ledge of the spar, and it's glued to the bottom one, which is glued together, and then it's glued to the bottom of the spar on top. So what we've done is our skin is a 1-piece skin. It starts at the back, totally wraps completely around the spar, comes back, and there's one glue joint back there holding 2 skins, the opening shut. It is also bonded all the way around the spar. So the glue joint is doubled in size. There's much more contact surface, much less chance of failure with that. Because of the way the blade's made, we've got some paperwork. I know we have some here, the test we did. Jimmy might have some. I haven't looked at all your paperwork, but you'll see that compared heads up. You probably don't have this because we did the heads up against the bird blade we used before, the dragon wings. The amount that the blade droops, the torsional testing on the blade, it far exceeds what Ernie's blade would do. And if you look at the test lines, those lines are very straight and linear, where Ernie's were a little bit like this. So it's just, the only thing that tells you is that it's a more refined blade. And when we manufacture a blade here, the manufacturing process is documented. We set it up so it's documented from the very beginning. So we machine all the parts. They're all machined at the exact same size. Put it in the mold. We cook the blade off. The blade is removed. But during the cooking process, thank you to Philip Blaha, I don't know what Philip is. Easier somewhere. Philip developed the computer system that drives the oven on the blade. There are 6 zones on the blade mold, and there's 12 points of measuring temperature. During that whole entire cooking process, each one of those temperature sensors is sending data back to the computer, and it's logging it through the entire cure process. So when that blade is done, we can print that sheet out, and we can look and make sure that we have not exceeded temperatures or time based on the manufacturer's recommendation. To give you, for instance, the glue, as you ramp the speed up, it cannot exceed 5 degrees a minute. It has to be kept below that on the ramp-up time. Once it gets to 250 degrees, it has a dwell time of 75 minutes, and it has to hold that temperature within a couple of degrees. With the computer-controlled oven, we can do that, and we can document it. Going back to Ernie now, he used the same glue, but Ernie had an open mold and an egg timer, and that's how he cooked the blades. He was very fortunate because he really built a good blade. He didn't have them come apart, but he could never prove or document what went on with each individual blade. So now you have a blade that is serial numbered, documented throughout the entire process. When the blade is done, we make the blade at 115 inches. On the XE models, the blades are cut down to 110 inches, so we have a 5-inch flap in the end. We use that for pull tests. So what we do is we cut a 2-inch coupon, they're always the same side off each blade. We develop a fixture for our hydraulic press that we can actually hook to the blade and pull the glue joint apart and see where it comes apart. Okay? Doing somewhere between 10 15 tests on underneath blades. The pull test will go about 50 pounds. It averages between like 48 and 52 pounds is where it yields. That was the standard. That was the bar we had to set. Last week's blades that we run, we had them go as high as 82 pounds before they come apart. But if you have to average it, we're averaging somewhere 60, 65. So again, we have exceeded what the old blade was structurally where it comes apart. I tell you all this to give you confidence that the blade, we just didn't wake up one morning and decide we're going to make blades and let's just go see if these will work. I mean, we really, it was a 3-year process. I mean, the guys that know us, and while they know the struggles we went through, from buying machinery, making machinery that you can't even buy, and fortunate for us, it came out fairly well. Now, Jimmy is now going to take the mic, and he is going to give you more detail on the testing that he done. We made a blade, sent it to him, and he has machinery built and fixtures built where he can just destroy the blades. So now that's what he's going to talk about. All right, Jimmy McCutcheon.
Let me tell you about these guys. They are the best. I mean, I've been building stuff forever. These guys have an attention to detail and a desire to do that extra, even if it's expensive, to do the right thing. And they're good. They're a pleasure to work with. Now, like he was saying, I've been messing with rotor blades since '84, and if you, on different machines, a lot of auto gyros, a lot of helicopters, if you lined all the blades up that I've made or caused to be made, you know, 20 miles, right around 20 miles of them, and that's, you'll learn a few things. I'm not, don't get me wrong, I'm not the, you know, I've had a bachelor's degree in mechanical engineering since the early 70s, and I'm not the finite element analysis guy, but what I do excel in is cost-effective experiments, you know, cost-effective test procedures, and I got that down, and so that's, these guys, they didn't want me to just tell them what's good and what's bad. They know it's good, they wanted to know how good. And it's good, you guys are lucky. I've never seen anybody in the manufacturing blade business for experimental industry go to the extents that these guys do. They get extrusions from the extruder, aluminum extruder spars, and then they'll go ahead and machine those in addition to up the tolerances more than what it came for. Nobody does that except these guys. They really pay attention. So what they wanted me to do, I've got some really big equipment for pulling on things. They wanted me to take a good look at this spindle, its root attachments, and the blade from about here to here. And it's good. Now let me tell you a little bit about the stresses. You know, they said don't go into too much detail with numbers and stuff, kind of broad strokes. What I just heard was detail. So I think that's a bunch of bullshit. So I'm going to get into a little bit more detail than I was thinking about originally because Dwight does. And if anybody wants more detail than that, then you give me when I'm done, and you know, as far as where did that number come from or how did you get that, I'll show you. this is a, let me take the stress on the skins first. The top and the bottom skins, 60, 61, T6. Now when you load put tension on a rotor blade when it's spinning, and the RPM they're dealing with right now, the tension is about 10,500 pounds. Now when that is, and they've got this spindle that's set at 1.79 degrees with respect to the axis of rotation. When you're running the blades up at zero lift, zero G condition, the blade comes out at 1.79 and then it goes out straight. So you've got bending on the additional tension on the top skin, reduced tension on the bottom skin, and it makes a difference. When you're at 1 G of flight condition, the blade lines up with 1.79 degrees and you have no additional bending stresses. 2 Gs, you've got the same situation as 0 Gs, but it's reversed. Now, the FAR Part 27, the Federal Aviation Administration, says they want to see 2 Gs with a factor of safety of 1.5. So remember that. 1.5. Yeah, that's a good one. And you think of aircraft, one factor of safety of 1.5, that seems kind of little. Space shuttle was 1.05. You bolt something to the bottom of a car, an automobile, it's like you can get a factor of safety requirement of 6 to 10. And what it is the loads, they're unpredictable on a ground vehicle. You don't know, hit a speed bump, whatnot. In the air, the thing is built to handle certain loads, and so the factor of safety goes down, and don't get loads that exceed that. But it's getting back to the stress on these skins. It's tough to figure out. It doesn't have a flapping hinge. It's whatever happens is dealt with by bending, and it's a complicated to do it. Do it just number-wise. You'd have to know where the effective flapping hinge is, and it would be like if it did have one, it'd be out here someplace. But without its exact location, it's really tough to do calculations to determine the stresses on the top and the bottom skins. And the most accurate way to do it is with a strain gauge. If you measure the strain on something, you can calculate backwards and get its stress on that item, because tensile modulus equals stress over strain. Remember that one?
Yeah.
And tensile modulus for aluminum is a well-known thing. So I've got this great big fixture. It's a box tube. It's 10 inches by 10 inches, maybe 12 by 12, about 1 inch wall thickness with it was a piece of I-beam with the sides welded in is what it was. And you can treat that as a piece of the earth. I mean, it's there, it's not going to flex with these kind of loads. Really, really solid. And that's what I set this particular deal up with. It's got a hydraulic jack on one side that'll go to 100,000 pounds, and I've got it set up to pull instead of push. And then a 100,000 pound load cell, which goes in 1 pound increments, very accurate. And then I'm pulling on the tip, and I've got the root of the thing held in a big welded steel fixture that grab this. Well, the end result is I grab the spindles with this spindle attachment plate right here, and I was able to rotate that fixture in the coning mode, let's call it, up and down for 0 cone, plus cone, negative cone, so I could see what's going on there. And I made a mechanical, I didn't have a strain gauge, but I made a mechanical one that would read pretty accurate, because the blade skin is flat, and it's easy to put a flat thing on top of it that would measure actual deformation of the skins. and work backwards from to the stress. So at zero load, where it's bending down, actually, the stress in the top skin was like 12,000 psi.
Microphone.
Oh, I'm sorry. Yeah, the combined stress on the top skin would be 12,000 psi. Bottom skin would be 4,000 psi, around there, 4,300. So you got a safety factor on the top and the bottom of, well, the bottom was 2.46, and the safety factor on the top was about, pardon? Yeah, it's about 2.5 or so. And that's compared to a yield strength on aluminum of 30,000 psi. Now the published yield strength on 6061 T6 is from 30 to 35,000 psi, and we use 30,000 just to be on the safe side. So at 1 degree, or at 1 G, when the blade's in line with the coning angle, about 8,000 psi, something around there, 8,000 psi. And then at 2 Gs, it was the same as the load for 0 Gs, but it reverses itself. The bottom skin's got the most tension, and the top skin is reduced, actually about 4,000, because it's got a little bit of, takes it away. So all of those figures are well within the realm of what the FAA requires. It's not a fatigue issue because they're not reversing stresses, they're not fluctuating stresses that go from nothing to maximum at any kind of a period. They're just, when you take off, they go up, when you land, they go back down. So it's not a real concern for fatigue issues. Plus, aluminum is considered a real ductile material and is less susceptible to fatigue than, well, actually I can't really say that, but it's a ductile material, less susceptible with holes and stress concentration factors. But it is a material that has no lower fatigue limit. There's no lower endurance limit. If you have a piece of aluminum and you sit there and you bend it back and forth, no matter how much, at some point it'll fail. There's no lower fatigue limit. It's like steel. At some point, stress-wise, you keep bending it, and you can bend it forever, for infinite time. Not so with aluminum, but it has to be a fluctuating load. So then, what is really the interesting part is, let me make sure I covered all of those. Huh?
I've been watching you guys.
Okay.
Down to the plate,
Right. Oh, my little, I wanted to tell you the strain gauge that I used, came up with, and it was,
You got a picture of it, right? Don't we have pictures?
I do, but I don't, you got it in there?
Yeah. When you get through the blade bolt, we'll go through the pictures.
Well, show me the strain gauge right now. I'm going to talk about that. It's really cool. Okay, that's there's the beam.
You gotta talk to the microphone.
There's the beam, the fixture that's bolted at the top of it. It's got a pivot point right here. Bolts up, that bolts jack it up and down. Pivots right here, so it does this. Spindle. On all these measurements, I consider the spindle bolt attachment plate to be fixed with this structure right here, and I called that's a reference. That don't move. What does move, well, here's the big issue. Listen up. Louder.
Yeah.
Just hold it.
Only now.
Louder,
Right.
Mr. Speaker.
Aye.
Yeah.
Yeah. Makes me want to burst forth with song.
A little crawl under the table.
You know, when you got this set at 1.79 degrees, and you're pulling on this 10,000 pounds, and you think that's going to, right here, it's going to be pretty damn 1.79 degrees. It's going to be rigid. This piece right here, at that kind of condition, will lose about half of that cone. There's about a degree of flex, of elasticity. It doesn't get up into the plastic range, but it's elastic. From here, from this backing plate to this surface right here, you can lose about a degree. Huh? 0.9, yeah. and that makes it makes the loads on the skins go down. It's like they got a flapping hinge rotor for nothing. You know, there's no real, just elasticity in the material, and it's a good thing, because when I was first started doing this and I was setting it at 1.79 degrees, I had a aluminum block right